Hello, welcome to Mechan 2040 Solar Mechanics. I am Globus. In this tutorial, we will discuss about deflection of beams. So the following is the agenda of this tutorial. Basically, at the very beginning, we will try to derive the integration relationships or differentiation relationships between different components or different properties of bending deflection problems. So we will try to derive those equations in terms of radius of curvature, etc. And basically for 7.1 we are talking about integration method, so later on you will know it. Also, we will introduce a very important method called superposition, and it is based on the table lookup technique. So I will also teach you where you can find the table. It is in the appendix of the textbook. By using the table lookup method, you can greatly simplify the process of solving the beam deflection problems. So on top of the integration method, we will introduce a very convenient function called Singularity Function. When we apply such a function in beam deflection problems, it will greatly simplify the problem solving process due to its unique properties. So we will introduce to you later on. Also, we will discuss about deflection of non-uniform beams. The stress will be placed on some special boundary conditions because in case of non-uniform beams, the moment of inertia could change. So we have to take into consideration such kind of change and such impact at the boundaries. Finally, we will talk about statically indeterminate beams. So it could be very challenging, but believe me, after this tutorial, I think you can master all those topics. Hope so. So in this section, we will talk about integration method. It is one of the most common way to deal with beam deflection problems. So actually, consider we now have 5 marbles, and we are going to connect them by using a string. So those marbles respectively represents the load, the shear force, the moment, the angle of rotation, and the deflection curve y. So while we go through different kinds of proof, you will see how those properties inside a beam or the shape of the beam will be interrelated to each other. So first, let's talk about the relationship between the load and the shear. So now load is W and the shear is V. So now those two marbles can be connected together. Okay. So consider a beam under an arbitrary distributed load, and we take a very little segment out and we magnify it to discuss about its equilibrium. So here we discuss about force equilibrium in the vertical directions. So we take upward as positive, so downward force are negative. So on the left hand side of this little segment, we have a shear force V pointing upward, so it is positive, like this. Okay, so on the right hand side of this element, we have a shear load V plus delta V pointing downward, so it is negative. So we subtract this amount from V. Okay. Besides, in this schema, we know that for this distributed load, the total load is given by W delta X, where W is the average value on this little piece of stress element. So we assume W is an average value of stress intensity, and over the short length of delta X, you can get the total load in terms of force unit instead of stress unit or the stress intensity units. Okay, so by getting W delta X, you get a downward force, so you subtract it. Then you try to simplify this expression. You know that delta V equals to minus W times delta X. If we write the delta into the differential form, then it will become an important equation marble, which is dV dx equals to minus W, means that the external load equals to negative of the derivative of the internal shear force with respect to x. So just now we have the load and the shear force, those two marbles connected together. Then we will connect moment as well. So moment and shear will be connected in this derivation. So consider a beam, still the same beam, the same element, but instead of considering the force equilibrium, we consider the moment equilibrium at some points. So to simplify the computation, we take the moment equilibrium at point C prime. So at the point C prime, if we take the clockwise moment as positive, okay, so at this side there is a clockwise moment m, and on this side there is an anticlockwise moment m plus delta m. So those two moments will cancel each other to get minus delta m. So as you can see here. Then for the V plus delta V load, we know that since we are counting the moment at C prime, so this shear load will generate no moment on this side, but the shear load, the upward V at point C, will generate a moment of V delta X, which is clockwise. So we plus V delta X over there. Finally, we count the moment generated by the distributed load. So for the distributed load, we know that the total load is given by W delta X. And if we take the average again, we know that its equilibrium or its equivalent position is located in the middle of this differential element. So we know that the moment generated is given by the load W delta X times the distance of this equivalent load, which is 1/2 delta X from C prime. Finally, we know that this load is generating an anticlockwise moment on this force element, so we have a negative sign. So this is why we have this term over there. After we simplifying this equation, we will get the equation below, which is delta m equals to V delta x minus W times delta x squared divided by 2. However, in the differential analysis, since this delta x is of the second order, so we know that delta x is a very short length in comparison to the whole length of this beam. So once we are talking about delta x squared, a very small quantity squared will become an even smaller quantity. So this term will be regarded as 0. And finally, we get delta m equals to V delta x. Finally, we move the delta x to the left-hand side as well as write it in the differential form. We can get dm dx equals to V, which means the internal shear force inside a beam equals to the derivative of internal moment with respect to x. So for this marble, just now we know that W equals to minus dV dx. Now we know that V equals to dm dx. So as we can see, those three marbles are now connected together by using such kind of differentiation techniques Okay, so those equations will be frequently used if you are just using integration method to solve the problems, but later on you will notice that the integration method could be very troublesome, could be very crappy, the solutions could be very long. But anyway, those are foundations of the beam deflection theory, and it's worth you to remember. Next, let's talk about how to connect the moment to the deflection curve. So by introducing the way to connect those marbles, we will introduce you a mathematical concept which is not covered, probably not covered in your previous taken mathematics course, which is called radius of curvature formula. It is a mathematical concept that worth you to know, but to be honest, it is very unlikely that it will be tested because it is more stressed in mathematical computations instead of solid mechanics, and you know our course is talking about solid mechanics, not mathematics. So the following derivation is just for your information. Don't take it too serious. If you don't really get the radius of curvature things, just ignore it. So basically, the idea is that we try to express the radius of curvature by using first and second derivatives. So how to do that? So here is an example of radius of curvature. So say the curve y equals to x to the power 4 minus 2x squared plus 3, and we are taking the radius of curvature at those points. Okay, so this is already the results given by this author. So I found this picture from his website. You may want to have a look for more information about radius of curvature. So basically, it is talking about the radius of curvature of the curve at some specific points. Say at x equals to minus 1, the radius of curvature for this curve is 1/8, and the same for the rest of them. So now we are going to derive the radius of curvature formula by considering an increment of length ds along an arbitrary curve. So for an arbitrary curve, so here we introduce a curve which is plotted in purple color. Okay, I hope you can observe it carefully. It is a purple curve, or I try to draw it. Try to draw it as accurate as possible. Basically, it is a curve like this. Okay, so bear in mind with that. So because such kind of derivation, it is in differential level, it could be very hard to draw the diagram, or I have to magnify this plot, say the delta thing is very large, so that you have to understand it. But anyway, by some common sense, we know that an increment of length ds along the curve is given by, so for example, you have a curve and you want to know the length of this curve. So say you want to know the segment. The best way to estimate is to get the dx and the dy, and you compute the approximate length by using the Pythagoras theorem. Bear in mind it is approximate length. Okay, so in case we are talking about differential amount of length, then we really treat this very short segment as a straight line, as we're talking about differential level. So an increment of length ds is given by the square root of dx squared plus dy squared, and we take out dx, then the terms inside the square root will become 1 plus dy dx squared, but y is just fx, so we just write df dx. Okay, So the angle between the x-axis and the curve, so actually it is the angle between the x-axis and the tangent to the curve at certain point. Say here, we take this point and we take the tangent, which is here. Then we can get an angle between this tangent and the x-axis. So this angle is given by the arctangent of dy dx. So it is just arctangent of f prime x because y equals to fx. Then, by using some differentiation techniques, we try to find the d gamma dx. So we apply the chain rule that d gamma dx equals to d gamma df prime x times df prime x dx. Okay, but when talking about d gamma df prime x, we have to apply this formula because we know gamma is a function of f prime x and we can differentiate it with respect to f prime x to get this term. We retain this term, and for this term it is f prime x. Once it is differentiated once again, it will become the second derivative, which is f double prime x. So all in all, we will get the result that d gamma equals to f double prime x over 1 plus f prime x squared dx. So what is the importance of this result? So in the following, I will show you. When talking about the radius of curvature, we will think of, at this point, for differential length ds, what is the radius of curvature? By estimating the radius of curvature, we have to use the arc length formula of a circle, which is given by rho delta gamma equals to delta s. So you can refer this equation as a variation of s equals to r theta. So I believe you learned it in secondary school as well. Then we try to rewrite this arc length formula in another form, which is we take the reciprocal of the radius and we throw anything to another side. So we rewrite this one to get this one, and finally we write it in the differential form. From the previous slide, you know that d gamma equals to this whole bunch dx, right? But in the very beginning, we know that ds equals to dx times 1 plus f prime x squared. Okay, we just write it in another form. So if we move this result to here, the ds, then you can see the dx here can be cancelled out. So eventually you will get the very important radius of curvature formula in terms of first and the second derivative of a function, which is given by 1 divided by the radius of curvature equals to the second derivative of a curve divided by 1 plus the first derivative of a function to the power 2 and the whole bunch of things to the power 1.5. Although we obtain this equation, it is complicated. Later on, we will try to simplify it. Before we simplifying it, I have to mention one important equation we mentioned in previous tutorials, which is talking about the radius of curvature as well as the moment inside the beam. So in tutorial 4, we know that 1 over rho equals to m divided by ei. So if you don't know where this equation comes from, you can refer to tutorial 4 for information. You know we have 1 over rho, we also have m divided by ei. So we can write the whole equation in this way. And actually, 1 over rho is just a supplementary character. It is not the main character of our movie. The important thing is the moment. This is how we relate the function y to the moment. Okay, so now the deflection curve y somehow has some relationship to m, and we are going to apply it in our solid mechanics problems. But before we apply it, we will try to simplify it by doing some very important assumptions. The assumption is that when we are doing the beam deflection problem, we do not expect the deflection curve to be like this. For example, you have a beam like this, then no, this is not in our consideration. We are now considering a beam, for example, a very small deflection. When there is a load applied, then it could be deflect downward a little bit. Okay, it would be small, not that large. So based on this very important assumption, we can now cancel this out. The whole denominator will become 1, and now we have m divided by ei equals to y double prime x, which means m equals to ei y double prime x, and for the rest of them, since they are interrelated by the derivatives, you can write them like those, v and the minus w, those things. Okay? So after we're talking about the relationship between the moment and the second derivative, I will introduce you something about angle of rotation. So you know, a beam subject to external load will deflect. For example, the beam could become like this. Okay, so this distance is called deflection, the distance between its original shape and its current position after a load is applied. But if we talk about angle of rotation, here we are talking about the tangent. The tangent, say at this point, the tangent could be like this, a little bit oblique, okay? And here is the angle of rotation we care about. So in short, the angle of rotation is just the slope of a deflected beam, and to find it, it could be very easy. In case you have the deflection curve, then you can just differentiate it. So for the deflection, we know it is yx, and for angle of rotation, we just take the first derivative, theta equals to y prime x, and based on still small deflection assumption is very important. Based on this assumption, for small theta, you know, y prime x for any curve, originally it equals to tangent theta. Okay, but for small angle, by small angle approximation, it is approximately theta. Then you can write the equation like this. So let's do a short summary about the integration method. So just now we mentioned about the moment, shear force, and external load. They are all interconnected by some derivative relationships based on the statics of a single stress element extracted from a long beam. Okay, when we relating the moment and the deflection as well as the angle of rotation, we adopt the radius of curvature formula. So y and the moment are connected by radius of curvature formula, and from y to theta is just theta equals to y prime, and the same for moment, shear force, and the w, the external load, they are just kind of connected by some derivatives like v equals to dm dx, w equals to minus dv dx, something like this. So in differentiating order, it looks like this, and in the integrating order, it looks like this. And when we solve the beam deflection problems, very often we will start from the moment, because moment is one of the easiest things we can compute by the given load conditions and the support types. Okay, so you know, if you integrate just from the external load, then you might ask, how could you express a single load in terms of a function? It could be very difficult to do that. Okay, so very often moment is a very important thing to do while we are solving the beam deflection problems. So it is a very common starting point, and by integrating it twice,
you only get two unknowns.
And very often in every beam deflection problems, you can get two or more boundary conditions that support you to solve C1 or C2. But if you just begin from the external load, then apart from the difficulty of expressing the single load, you also have the difficulty of solving those four unknowns, which could be very time consuming. So as I introduced just now, when we solve for the unknowns from here, say C1 and C2, we will use the boundary conditions. So in this course, we often deal with those boundary conditions. The first is the simply supported end. The simply supported end means that there is no deflection at this end, or in some very special case, if the problem says, okay, this end, say, okay, is moved downward by some distance, then the deflection at this point can be defined in another way. That is another story. And when talking about the cantilever beam, which is the fixed end, we have two boundary conditions here. One is about the deflection. The deflection is 0 at this end. Another thing is that we assume there is no angle of rotation in the fixed end. So y prime also equals to 0, because you know theta, the angle of rotation, equals to y prime, the derivative, the first derivative of the deflection curve. Okay. So in this example, we will try to prove some entries in superposition table, which is a very important table. And we are going to prove the accuracy inside this table by using the integration method. So the first problem, we are dealing with a cantilever beam with uniform distributed load of intensity Q exerted on it. So the major results to verify, including the deflection curve, the deflection at the end, the angle of rotation, etc., as well as the angle of rotation formula. So to verify this entry, first we start from the moment inside the beam. So we cut the beam over there at an arbitrary position x, okay? Then we take the right hand side beam and we take the moment inside. Then the moment will become something like this. Okay, since in this tutorial we are talking about the beam deflection, so I try to skip those things faster than previous tutorials. Okay, so the same, after you get the moment, you will do some mathematical integration. EI theta x now becomes something like this. Notice that we have an additional C1 after integration. However, if you apply some boundary conditions, such as theta 0 equals to 0,
This boundary condition means that the angle of rotation at the fixed end equals to 0.
okay, then you apply it into this equation. Then you can find the value of C1, which is minus QL cubed divided by 6. And if you further integrate this one plus C1 to EI deflection curve, then it will become something like this. You have another C2, and the same thing, you repeat it once again. You apply the boundary condition V0 equals to 0, then you get C2, and then you get the deflection curve. So notice that here in the superposition table, they like to express the deflection curve in terms of single term v, or the same, the y, okay, on the left hand side. But here we have EI next to it. This is why you found that, okay, why there is no EI in the denominator. So after you finish finding C2, then you just write down the whole things, as well as make the denominator of each term the same. Then you try to expand this polynomial, and you can get this result. Okay, and for v prime, similar, you can just differentiate it, or you just take it from here. Okay. For delta b and theta b, you just substitute the value. For example, because for this beam, we know that the length is L, so we just put L into Vx to be VL. So we find VL and theta L. Then we will get the result of delta b and theta b, where b is just the free end. Okay, so notice that although after you're substituting the whole things into VL and theta L, you will get a negative value, but the negative value means that you are true, because in the superposition table here, as you can see, there is a sign convention, means that the deflection curve very often will give you a negative value when there is a downward distributed load, but when talking about the deflection, we will count downward as positive, so no worries about it. Okay, so here are just some steps showing you how you make all those things get proved. Okay, so I leave you to read yourself. Next, let's talk about the method of superposition, which is a great way to simplify the problem-solving process by using the table checkup techniques. So, this technique is particularly useful when you are analyzing a beam with a lot of loads, because you know, for a lot of loads, you could write very, very long moment equation. For example, you have a beam like this, okay, and you have load here, 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 and maybe you will write mx equals to a very large bracket, some function, and some domain, some function, some domain. No. When talking about method of superposition, you can find the deflection curve, the deflection, or whatever things in a very convenient way. I could say it is much more convenient, but in terms of computation, it is not that really convenient. Okay, but all in all, the method of superposition, the table checkup method can simplify the process a lot. So some important results are already tabulated for your quick reference. So those results are already computed by other solid mechanics scholars, and it can accelerate your computation. So you can find it in the textbook, and in case we are going to use some entries of this table, I will also show it in this PowerPoint slides. So now let's consider a very complicated cantilever beam. It has three loads. One is the single load located at position A divided by 2. Another one is the distributed load W, distributed from A to 2A, as well as a moment at point C, which is the free end. So they have different magnitude, and of course, if you try to solve it by using integration method, I highly believe that you will cry. But you could try. I also tried, but I will not really post the process I tried because it really takes time. Because even though you solve it, you cannot guarantee that there is no error in your steps. And once there is any error, then the whole thing is 0. So actually, to solve this problem, I use 1 whole month. I could say, okay. But later on, I will teach you a hack, the way how to solve the problem even faster, still by using the integration method. So, return to this problem, we are going to use the superposition method to solve it, and the way to do that is to do the table checkup. First, we know that for this beam there are 3 kinds of loads, so at the very beginning
We take out one of the loads.
Okay. So here we know that in the superposition table, the table says the length is L. Okay, but in this problem, we are talking about that the length now becomes 3A. Okay, it could bring you some confusion on the application of this table, but you have to be careful. Or, to get rid of confusion, we let L prime equals to 3A, and of course the A prime equals to A divided by 2, because the A here in our problem do repeat to the term in the table, so I try to simplify the things. So now we are looking for the deflection at the free end C, as well as the angle of rotation. So to do that, we first notice that the deflection at free end, okay, due to the single load P is given by PA squared divided by 6EI bracket 3L prime minus A prime. So still, now we put everything into the equation, but ensure that you are doing all the things carefully. You cannot make any mistakes. Okay, so P equals to 3WA divided by 4. A prime equals to A divided by 2. And here it is A squared, so A prime squared as well, divided by 6EI. Okay, so 3L prime equals to 9A. Okay, and here it is A divided by 2. So eventually, you know that the deflection at the free end caused by the single load P is given by 51 WA to the power 4 divided by 192 EI. And similarly, for theta, for the angle of rotation at the free end, due to the single load P, you do the same thing, you substitute everything inside, then you will get this. So for the next, as the distributed load in the middle, it is a little bit indirect because from the superposition table we don't find other entries that describes a distributed load in the middle. However, to analyze this distributed load in the middle, we can try to use 2 distributed load from the fixed support, which are canceling each other to get the equivalent deflection at the free end. So we know that here we have the equation. So we will try to subtract the deflection caused by those area, okay, from this longer distributed load. So the way of substituting the numbers are just similar. To avoid the confusion, let L prime equals to 3A, Q equals to W, A2 equals to 2A, and A1 equals to A. So here it is A1, here it is A2. So the deflection caused by this distributed load equals to the longer one, the downward one, subtract the upward one. Okay, then you substitute the numbers and simplify it. You will get 69 WA to the power 4 divided by 24 EI. The same for theta, and you will get 7 WA cubed divided by 6 EI. Finally, we talk about the moment, but still the things are rather similar, except that we know in the table m0 is positive in this direction, but here the moment is counterclockwise. So m here will become minus. So here there is a minus sign in front, and after we substituting the moment inside, we will get delta m and theta m. Finally, we just need to sum up all those deflections as well as the angle of rotation caused by those individual loads. Then we will get those two solutions. Okay, so for those two solutions, I am very confident because for me, I have already verified once before by using the previous prescribed integration method. So after we're talking about the integration method as well as the superposition method, now I'm going to introduce you a very important function called Singularity Function. It is very important because it can greatly simplify your analysis of the beam deflection problem when using the integration method. As what my friend says, the singularity function is simply a hack of those beams with a lot of load conditions. Okay, so the singularity function is given by the corner bracket x minus a to the power n equals to the round bracket x minus a to the power n if x is greater or equal to a, and it is equals to 0 when x is less than a. That means if the value inside the bracket is 0 or positive, then the singularity function will work. Otherwise, if inside the bracket the value is negative, then the singularity function will just simply return you a 0. Okay? The meaning of the singularity function is that the mathematical term caused by certain element occurs when x is greater or equal to a. But you know, if x is equal to a, then it is just 0, so there is no very large difference. Okay. But one important property of singularity function is that when you're differentiating it or integrating it with respect to x, its performance is very similar, or I can say it is almost the same to that of the round bracket x minus a to the power n. So you just need to treat it as a simple function, and then you differentiate it, and the outcome is still n times the singularity function to the power n minus 1. Okay. So the same for the integration. So those properties enable us to apply it in the beam deflection problems with large ease. So in the following slide, I'm going to introduce you how to solve exactly the same problem as what we introduced just now, the cantilever beam with 3 loads. by using the singularity function. So just now we solved this problem. We found the deflection at the free end, okay, by using the superposition method. So let's now use the singularity function to verify our results in the previous example, okay. So you will later see that by using this singularity function, the problem can be greatly simplified. So to solve this cantilever beam with singularity function, we will need to modify this free body diagram a little bit, as shown in the blue color, those things. Okay, so the reason why we will modify it is that for the singularity function, we have beginning, but we don't have ending. That is, for a singularity function, x minus a, x is greater than a, it means that once the function starts working, it will work forever, but the reality is that for this problem, we only have a distributed load in the middle, so this term might bring us some challenge on the application of singularity functions. But anyway, let's start working segment by segment on this cantilever beam. So in the first segment, we will consider here. Okay, so there is a moment. So we've already got the support moment and the shear force at the fixed end by using our knowledge in statics. That is m0 equals to minus 3wa squared divided by 2 and v0 equals to 7wa divided by 4. So what we are going to do is to compute the moment for a cross section cut here. So the moment, the first thing is that we are going to cancel out m0. So mx equals to m0. Also, we will need to consider that there is a shear force v0 at the fixed end, which generates a moment of v0 times x. So we have to cancel it out as well. So we plus v0 times x. So this is the moment in the segment from 0 to a divided by 2. So after that, we are going to move our concentration to behind this single load P. Now, what we do is that we cut the beam over there and we consider the moment here. So still, this moment is going to cancel the moment generated at the fixed end. Another thing is that from a over 2 to a, you will have another load, another moment to cancel, which is P equals to 3wa divided by 4. But we have to bear in mind that the moment generated by P equals to P times x minus a divided by 2. Okay, but notice that this term, P times x minus a over 2, only occur after a divided by 2. So we can rewrite this round bracket to corner bracket. Also, we found that for the P, the moment generated will be also counterclockwise. That means in order to cancel it out, we have a minus sign. So far we have discussed the moment from 0 to a. So how about when we enter the distributed load region, what is the moment generated by the load inside the beam? So let's move our concentration to here, somewhere in between a and 2a. Say here, shall we? Okay. So here we have m moment. So similarly, this moment will need to cancel out the moment generated at the fixed end, as well as the single load. Okay, so we have already considered them. The distributed load on the left-hand side of this cut cross-section is given by W times corner bracket x minus A. Also, the resultant of the distributed load will be located in the middle, right? So it will be a distance of x minus A divided by 2. So we can write in this term. And also, for this distributed load, it will generate a counterclockwise moment. So similarly, we will add a minus sign in front of it. Okay, so the equation now will become minus W x minus A squared divided by 2. Now it's time to take into consideration of our modification to the three-body diagram. The reason we add these blue things is that for the original three-body diagram, we see that there is only a segment of distributed load in the middle, but for singularity function, it will start from A and it will never stop. So that means in case we write down this term, that means this term is accounting the moment generating from A to 3A, which is not reasonable. That means we have to get a cancelling moment starting from 2A to 3A, such that the moment inside the beam will be correct. But similarly, just now we mentioned how we could write the distributed load, the moment generated by the distributed load. So what we do is that we add back W times x minus 2A squared divided by 2, because the cancelling moment starts from 2A and it generates the clockwise moment. So instead of subtract sign, this time we will have the add sign. So finally, we will get this moment equation. Moment equals to v naught x plus m naught minus p times x minus a divided by 2, then minus those two moments generated by the distributed load. And then we substitute all the things we need, the m naught, the v naught, the p, and the mc. Although the mc is not really important, but yeah, also we have w, okay? So we put everything into this equation and we integrate it twice, and we now get C1 and C2, okay? So as what we mentioned, integrating the singularity function is just like integrating a normal polynomial, so it will be okay. Finally, by our sign convention, we can write theta x equals to minus y prime x, delta x equals to minus yx. So for those two equations, we can finally write it in this term. And by the boundary conditions at the fixed end, y0 equals to 0 and y prime 0 equals to 0, we will have C1 equals to C2 equals to 0. Then we will get the equations of deflection and angle of rotation. Finally, we verify the results by substituting x equals to 3a at the free end into those equations. Then we will have delta c and theta c verified finally. So this is the way how we solve the cantilever beam problem with complex load conditions by using the singularity function. I hope you can have some practice on it, or if you're interested, you can solve this problem by simply using the integration method without using the singularity function. And of course you will find it very complicated, but in case you want to use it in the exam, then it would be a very good exercise for you. So now let's move to the next section about deflection of non-uniform beams. For non-uniform beams, the superposition method does not really work due to the variable EI, because in the superposition table, we found that in every entry of this table, y equals to something over ei times some polynomial, right? But for non-uniform beams, it is not really easy to apply the superposition entries into the problem. However, we can use our technique of singularity function to express the moment inside the beam and apply the correct ei to the moment equation with singularity functions. So the main thing is that how can you handle the boundary conditions at the joint of two different EIs. So next, I will give you an example of a non-uniform beam. So it is a Pascal-Moore problem. A simple beam ABC has moment of inertia 1.5 I, so it is AB, and I from B to C, okay, and there is a concentrated load acting at point B. We have to obtain the equations of deflection curve as well as the angle of rotation at A and C. We are also interested to the deflection at point B. So, how to solve this problem? The first thing, of course, we're going to do it by statics. From statics, we know that Ra equals to 2p divided by 3 and Rc equals to p divided by 3. So, we are going to use the singularity function to solve our problem. The moment inside the beam equals to Rax minus P, corner bracket x divided by L over 3. So in this segment, we know that it is 2p divided by 3. So for the moment here, it will be 2px divided by 3. Then for the segment after the presence of p, we will have a counterclockwise moment, which means we have to subtract it. It is p times x minus L over 3. But it is only occur after L divided by 3, so we change the round bracket to the corner bracket. But anyway, the things are similar to our previous example. This is how we use the singularity function. For 0 to L over 3, which is for AB, we have 1.5 EI. Okay, it is different from our previous example because now we have a non-uniform beam, so it is 1.5 EI. 1.5 EI, Y1. So for this segment and this segment, we call the deflection curve as Y1 and Y2 respectively. Okay. So 1.5 EI Y1 equals to mx equals to Rax, because for 0 to L over 3, there is no such term in the moment equation, right? And it will become 2px divided by 3. And you integrate twice to get something like this, C1 and C2 as well. You apply the boundary condition, y is 0 equals to 0, that is at x equals to 0, the deflection is 0. And for this boundary condition, it provides you the information that C2 equals to 0. However, now, although you have C2 solved, but for C1, you still remain unsolved. So next, we will solve for C1 by considering another section. So now we are going to consider another section, which is point C of the simply supported non-uniform beam. So for segment BC, we can write the moment like this. M equals to this, right? So since we are now in the range of L over 3 to L, then this corner bracket will become the round bracket later on. Okay, so EIY2 double prime x equals to moment equals to something like this, and we take out the common factor p divided by 3EI, so the things left inside the bracket is L minus x. Then we integrate it once to get y2, which is equals to this. And we also have a constant C3. However, we expect that the angle of rotation at point B would be similar for both y1 and y2, because in case of very little deflection, the deflection curve would be rather smooth. Okay, so we assume y1 prime of L divided by 3 equals to y2 prime of L divided by 3. So in the last slide, we discussed about what is y1, which is here. Okay, so we just substitute L divided by 3 into it. Also, for y2, we also substitute x equals to L divided by 3 into it. Then you will get such relationship. And eventually, you can write down the equation, which is C1 minus C3 equals to 11PL squared divided by 162 EI. So this is one of the equations that left us to solve. Now we try to integrate y2 prime once again, and so that we can get the deflection curve of y2 segment. Still, we apply the boundary condition over here is that the deflection at point B for left and right segments are the same. So y1 of L divided by 3 equals to y2 of L divided by 3. Then we can write the equation like this, which is very complicated. You can substitute yourself later on. Also, by boundary condition that there is no deflection at the end C, which means y2 at x equals to L equals to 0, then you can write another equation.
Now we have 3 equations to solve 3 unknowns, C1, C3, and C4.
So it is just okay. After resimplifying those 3 equations, we will get the following linear system. You can either use some Gaussian elimination or other ways to solve the linear system. But here I give my own way to solve the system. Is that we substitute 1 into 2, and we will get, after we get C4, we can put C4 into equation 3. Then it will help us to get C3 equals to minus 175 PL squared divided by 1458 EI. Then finally, we put our result of C3 into C1 again to get C1 equals to minus 38 PL squared divided by 729 EI. So all 3 unknowns are now solved, and the deflection curve of the entire beam, the entire ununiform beam, will be obtained. Okay, so after we put all those unknowns which is solved into those equations, the deflection curve equations or angle of rotation equations, we will get those 2 deflection curves for different domain, from 0 to L divided by 3, from L divided by 3 to L. Then we can find theta A, theta C, and delta B by substituting the location of them. For delta A, the location is 0. Okay, so we put it into y1 prime of 0.
And similar for theta C and delta B. So later on you can try it yourself.
So in the next section, we're going to introduce you the statically indeterminate beams. So some beams are statically indeterminate due to the absence of the support magnitude. That is, once you use your statics knowledge to solve for the system, you can see that the number of equations available will be fewer than the number of variables you're going to solve, which means it is impossible for you to solve the beam by statics analytically solely. Okay. Sometimes the number of unknowns is larger than number of equations, as I mentioned. So some of those extra loads will be selected as redundant. That is, we temporarily select some loads as redundant or something we pretend that we know, and we can simplify the problem-solving process. So we often use the method of superposition instead of integration method because although it really works, but it takes a lot of time to solve. Okay. Now let's solve this statically indeterminate problem. It is my past homework. So here is a continuous beam ABC with two unequal spans, one span and two spans. Okay. So one of them is of length L and another one is of length 2L. So it is supported by some simple loads. So this beam is simply supported, and also there is a uniform load Q acting on this beam. We have to determine the reactions RA, RB, and RC of this beam, as well as the deflection curve in segment AB. Also, you are going to sketch the shear stress diagram and bending moment diagram for segment AB. So now we can see that there are three unknowns in this problem, RA, RB, and RC. However, here we only have two equations. One is the moment equilibrium and another one is about the force equilibrium along the vertical axis. So you only have two equations, but you have three variables or three unknowns. That means you cannot solve the three unknowns simultaneously only by those two equations. So here I'm going to introduce you how to solve this problem. The first step, we are going to set some load as redundant. So at this moment, I would like to set RB as a redundant load. So now once we remove RB,
then this beam will become a simple beam with evenly distributed stress intensity, like this.
Okay, so by the superposition table, we can find the entry of the deflection curve as well as delta and the theta, whatever. So here we apply this superposition table into this problem, but a little bit different thing is that the length of the beam is of 3L. So we cannot simply put L, or we cannot simply copy the L over there. Instead, we have to put 3L for L. So this deflection curve will become something like this. And at point B, the distributed load, so point B is located at x equals to L. So the deflection at point B can be get by substituting L into x, so that we can get the deflection over there as 11QL to the power 4 divided by 12EI. Okay, so now we have already removed RB and we only account for the deflection caused by the distributed load. So here seems there is a deflection over there, but actually there is no deflection. We just count the effect of deflection by each load separately. So by only the uniform distributed load, the deflection caused is 11QL to the power 4 divided by 12EI. So the next thing to consider is that once we add back this RB, the RB is supposed to recover the deflection at point B to 0. So by taking this into the consideration, you have to use another entry inside the superposition table, that is the single load one. Okay, so in this case, A and B inside the superposition H entry. So A is L, B is 2L, and L now becomes 3L. Then we put every parameters into this entry. We can get the deflection curve within 0 to a. Okay, so from 0 to a, the deflection curve is given by this. That is, we put all those parameters into here, then we get this. After that, we put x equals to L into the deflection curve to find the deflection caused by RB at x equals to L. So it is given by 4RB L to the power 3 divided by 9EI. Then by using the compatibility at point B it says that the deflection caused by the distributed load as well as the single load RB, their sum equals to 0. Okay, so by solving this equation, we obtain from the previous slide 11QL to the power 4 divided by 12EI, as well as the 4RBL cubed divided by 9EI. So those things are summed together. They are equal to 0. Eventually, we can solve for RB, which is 33QL divided by 16. So far, as you can see, by using the superposition table, we haven't yet used any information from statics, and we have already got what is RB. So for RA and RC, they will be rather similar. By using statics, we have the equilibrium in the vertical direction, as well as the moment equilibrium. So by solving this system, we can get RA and RC separately. And finally, with everything known, RA, RB, RC are now all solved. And we want to know the deflection curve. So as we mentioned before, for this superposition entry, the curve is just talking about from 0 to A. That means the left-hand side span. Okay, for the right-hand side span, you will do some modification to obtain it. But so far, let's try to get the results for the left-hand side span. So the deflection curve comes from the results of superposition entries V1 and V2. So in the previous slides, we already got V1 and V2. So I've already copied those results over there. And next is that we are going to add them up so that we can get the overall deflection curve of this beam, which is something like this. You can check it yourself. Okay, so how can we? So this is the deflection curve for segment AB. And one more thing I would like to say is that how can we get the deflection curve in segment BC? So the way is that just now we have A equals to L, B equals to 2L, and the L becomes 3L. Okay, so to obtain the deflection curve of another side, you will do some substitution. Like you are going to, so forget about all this, and you are going to find when A equals to 2L, B equals to L, and L is still 3L, you put into this superposition entry. So for example, just now you have P over there of L, okay, and you get an equation, but you don't know the equation over there, right? So the way you can do it is that you move the P like over there, and the whole thing become 2L. On the right hand side, it become L, and then you get the deflection curve of the left hand side. Okay, then after you get the deflection curve, say V on the right span X. Okay, however, as you can see, for this deflection curve, it is still locating in between 0 to 2L, right? But you know, actually, this 2L corresponding to this region from L to 3L. So this deflection curve corresponds to this domain from L to 3L. In another word, after you obtain the deflection curve by using this configuration on the left hand side, then you have to move this curve. Say we have a curve, something like this. You have to move this curve to the right.
But it is still not the end. You still need to flip this function so that it propagates in the right direction. So it will leave to you as an exercise.
Just now we have already got the deflection curve for segment AB of the statically indeterminate beam. So to sketch the shear stress diagram and the bending moment diagram, what we do is to differentiate this deflection curve twice, as well as time EI in front of it. Okay, so the moment after we differentiating this and the time EI in front of it is given by Q divided by 48 times 6Lx minus 24x squared, and for the shear force it is a linear relationship, which is Q divided by 48 times 6L minus 48x. So as you can see, mx, so this one is a constant, and inside the bracket it is a parabola. So mx is of a parabolic shape, and we are going to determine its maximum and minimum. Okay, so we have to determine where the shear stress attains 0 at x equals to L divided by 8, because we know that the shear force is the derivative of m with respect to x. So shear force equals to 0 means that the moment attains maximum or minimum. So at L divided by 8, we guess the moment will reach its maximum or minimum, so we have to have a look of it. Anyway, let's compute some important parameters. Okay, so for a moment we're interested to m0 and ml, m0 and ml at A and B, of course. This is one of the most important elements we're going to sketch, as well as the maximum or minimum. We don't know whether it is maximum or minimum, but anyway, it is an extremum obtained at x equals to L over 8, and the value is QL squared divided by 128. Okay, and correspondingly we can have V at the shear force at different position. Okay, so as you can see, the moment inside the section AB is just a parabolic shape, and for shear force, which is the derivative of the moment, it is of a linear shape. Okay, so in the following page you will see how we sketched the shear stress diagram and the bending moment diagram. Okay, so basically for the green curve is the parabola, which represents the moment inside the section AB, and on the x-axis here means L. Okay, and for the vertical axis there is moment and V, moment and shear force, which is labeled here. So the result is that you are going to time the number. Say if we are going to obtain the extremum of the moment, then we are interested to here at x equals to L divided by 8. So the value is 1 over 128 times QL squared, because for this curve it is a moment curve, so it is talking about moment instead of shear force. But when you talk about at x equals to 1/8, at 1/8 of L, okay, say at this place, then the shear force inside the beam is 0. So yeah, so there is nothing very special, but for the shear force at x equals to 0, okay, the value is 1/8. Okay, so for 1/8 here, since we're talking about the purple straight line, which represents the shear force inside the beam, so we have at this place the shear force is given by 1/8 of QL. Okay, so this is how you can read this solution diagram I sketched for you. Okay. So now let us introduce you the last example of this tutorial. It is still a statically indeterminate beam, but only thing is that in this problem we are going to use nothing about statics but everything from superposition. So as you can see, the beam is simply supported, but there is a spring in the middle of this beam. Okay, the load intensity is Q, and the distributed load is over the entire length of it. So what should be the stiffness K of the spring in order that the maximum bending moment inside the beam will have the smallest possible value? And the requirement we set is that we are not going to use anything about statics. Okay, so still, to repeat, we are going to minimize the maximum bending moment inside the beam. So you know, for a beam, there could be moment inside it, something like this. Okay, I don't know how the moment in this problem looks like, but we are going to minimize the maximum value of the moment inside the beam. To minimize the maximum bending moment, we are going to find an optimal value of K, which is the stiffness of the spring. Well, if you still don't get any idea about what this question is talking about, don't worry, we just do as what we know so far. So to solve this problem, the first step is still we remove the load by the spring in the middle of this beam, which is RC. Okay, so we set it as redundant, then the whole beam will become a simple beam, a simply supported beam with a distributed load of intensity Q over the entire length. So by the superposition table entry, if we make the L to be 2L into this entry, then we can find V1 in this form, and we simplify it to get something like this, and we differentiate it twice and the time EI in front of it, so we get the moment inside the beam caused solely by this distributed load. So still, once you get the deflection curve, you will get everything you want, because everything is just like a necklace. Every marble are interconnected by some relationships. So one thing you have to bear in mind is that still you cannot forget the EI in front of the moment. Okay, so when I do this PowerPoint, I always forget about it, and it can be very fatal error when you are doing calculation. So anyway, the moment M1 inside the beam is now becomes minus Q divided by 24 times minus 24 Lx plus 12x squared. So I will simplify it a little bit later. And in the midspan, in the middle of this beam, we care about its deflection. So the deflection is given by delta L equals to minus of V1L. Okay, that means when we solely discuss about the distributed load in the middle, the deflection caused by the distributed load is given by the negative of V1L, which is 5QL to the power 4 divided by 24 EI. After we talk about the deflection caused by the distributed load, we are now going to consider a single load located in the midspan of this beam, which is RC. So still, we put P equals to minus RC, as well as L becomes to 2L into those superposition table entries to get the deflection curve for the left span of this beam. Okay, so for the left span, we put everything inside this superposition entry, we get V2, and we simplify it to get something like this, and we differentiate it twice, and we get the moment by times EI in front of it. Okay, so basically you get a deflection curve, then you differentiate it twice and time EI in front of it, and then you get the moment. So the deflection solely caused by the single load in the middle of this beam is given by minus of V2 of L, and we substitute the things inside to get RCL cubed divided by 6CI, which is negative. The reason is that you are going to push this beam upward by using a spring. That means the deflection is now negative. You are against the deflection caused by the distributed load. Now we can write a compatibility equation, which is the deflection caused by the distributed load delta 1 plus the deflection caused by RC, the spring delta 2. Once they are added together, it equals to the deflection of the spring. But we know that the deflection of a spring is given by RC divided by K. The reason is that if you have learned a spring before, you know F equals to Kx, where x is the deflection, okay? X is the displacement of the spring. So if we rewrite this thing to be RC equals to K delta L, then delta L is just RC divided by K, right? So you can write this compatibility equation, which will be important for our derivation in the later stage. So delta 1 is this, delta 2 is this. Once they're added together, you will get the deflection of the spring, which is RC divided by K. So let's see how can we use the techniques of superposition to further solve this problem. The thing is that we can use the method of superposition to even get the moment inside a beam. So we got M1, which is the moment caused by the distributed load, as well as M2, which is caused by the spring load RC acting upward to the beam. So the moment, the total moment inside the beam, is given by M1x plus M2x, and you add them together, and you can write it in this way. So M1 plus M2 equals to minus Q divided by 2 x squared minus 2Lx. Then you minus x RC divided by 2 times Q divided by Q. Then it will become minus Q squared x squared minus 2Lx. Then here you take out Q divided by 2. It will become x RC divided by Q, which is a positive sign. Okay, then you write it in this way. You take out x in the latter two terms to get RC divided by Q minus 2L times x. So basically you take out the x here and here. Okay, then you will get M1 plus M2 written in this way. So to find the extremum of the moment, we have to find the solution for the moment differentiated one with respect to x. So to do it, we differentiate the things inside the bracket. X squared becomes to 2x, and for the term on the right hand side, the x disappears, simply disappears. And m prime x equals to 0 means that x equals to L minus RC divided by 2Q In another word, the extremum of mx, regardless of its symbol, whatever, it occurs at the position where x equals to L minus RC divided by 2Q. So what is the significance? Why do we find something like this? It is because we are going to determine what is the extremum of the moment inside this beam. Okay, so with the moment equation we try to obtain the moment inside the beam by substituting 0 and L inside the moment equation, as well as the extremum we know. Okay, so basically we have a couple of things we are going to care about, which is m0 equals to 0, so at the fixed end there is no moment, and the moment in the mid-span ml, which should be the largest by our common sense when we observing this beam. So the moment in the mid-span is something like minus q over 2 times RCL divided by q minus L squared. Also, we are going to get the moment at the extremum we just now we already obtained. Okay. Now we have here, and here. Okay, those three things. Their value could be positive or negative, so we have to consider the absolute value of it. And now the question is that what is the stiffness so that the maximum bending moment is minimized? That means we are going to find K such that the minimum of the maximum among those three candidates should be the smallest. So to do this, since we are going to minimize the largest moment, we will have ml equals to something like this in the absolute value. It equals to the moment at the extremum. So in case one of them is positive, one of them is negative. Okay. So under this case, we can write the above equation. This one. Okay. One of them is in the absolute value, so there is plus minus sign over there, and another of them, since you know the bracket on the right hand side is already squared and the q is a positive quantity, so we can write the equation in this way: plus minus L times RC divided by Q minus L equals to L minus RC divided by 2Q squared. And we further expand the equation. If the symbol here is plus, then 4QL RC minus 4Q squared L squared equals to RC squared minus 4QL RC plus 4Q squared L squared, which means that RC squared minus 8QL RC plus 8Q squared L squared equals to 0, which means that it is a quadratic equation of RC. And now we are going to solve for RC such that the moment generated will be the minimum. So for this quadratic equation, it will generate two solutions, which is here. Okay. But if we consider the negative case, that is on the left hand side, it will become minus 4QLRC plus 4Q squared L squared. Then those two terms and those two terms will be cancelled for each other. Okay. Then the remaining thing will become RC squared equals to 0, means that RC equals to 0. So now you get another solution for RC. So now there are three possible candidates of RC. The thing we are going to do is that we are going to substitute each value of RC into this equation, the maximum of M0, ML divided by L minus RC divided by 2Q and ML. And for those three values of RC, I want to know which value of RC will generate the minimum value of maximum possible bending moment. So for example, if we have RC equals to 0 and we put it here, then ML absolute value equals to M of L minus RC divided by 2Q. It equals to QL squared divided by 2. Okay, FRC equals to 4QL plus 2 square root 2 QL. Then ML inside this bracket will become Q divided by 2. Then L minus RC, which is 4QL plus 2 square root 2. So to simplify it, it will become 4 plus 2 square root 2 QL. So once RC divided by 2Q, it will become L minus 2 plus square root 2 of L
Squared.
absolute value, which is even larger than this one. Okay. So this candidate is already eliminated here because inside the bracket it is L minus 2 plus square root 2, which is about square root 2 plus 1 L divided by 2 squared, L squared divided by Q. Okay, so it is much larger. So this candidate is now eliminated. So talking about when RC equals to 4 minus 2 square root 2 QL, then the moment inside equals to Q divided by 2 still, and L minus 2 minus square root 2 L squared. So the things inside the bracket will now become Q divided by 2 L squared times square root 2 minus 1 squared. And you know square root minus 1, square root 2 minus 1 equals to 0.4 something, and it is less than ML at RC equals to 0. So finally, RC equals to this. This candidate wins the competition that it can minimize the maximum moment inside the beam. So we have RC equals to 4 minus 2 square root 2 QL. So still, those equations come from this. So 8QL divided by 2 equals to 4QL. And in the square root, it becomes 4QL times square root 2. And for the square root divided by 2, then it will become plus minus 2 square root 2 QL. So here there is two solutions, which is 4 plus minus 2 square root 2 QL. So those are also two solutions. Okay. And among those three solutions, 0 and those two, we find one of the solutions such that the largest moment inside the beam is minimized. So for the largest moment, we know ml and m of L minus RC divided by 2Q will be the largest, because we know that m0 equals to 0, so it is not in our consideration of the largest moment inside, right? So anyway, the conclusion is that RC equals to 4 minus 2 square root 2 QL. And finally, with the RC known, we can now put our RC into the compatibility equation. And once we solve it, eventually we will get the value of K, which is 89.63 EI divided by L cubed. So this is one of the way how can we solve the statically indeterminate beam problem without using anything about statics, because particularly because that in this problem we don't need to know RA and RB, partially because they are of symmetric to each other, A and B. Okay, but still I want to say it is possible for us to solve the statically indeterminate beam without any knowledge from statics, but we can fully utilize the superposition table to do anything we could do. So here is the summary of this tutorial. So basically we talked about the relationship between the deflection curve, angle of rotation, moment, shear force, and external load. So they are just like 5 marbles that are connected by a string. Under many cases, you can start from moment instead of from load, so that you can reduce the number of unknowns to solve. Also, we introduced you a singularity function, which is very useful for you to solve the beam deflection problem without very crappy computations, and its unique properties can help you a lot. So for the details, you can refer to example 7.3. We also mentioned the method of superposition, which is a table checkup method, and we introduce you some concepts of superposition and redundant loads in statically indeterminate beams. And we also introduced an example of non-uniform beams. So basically, the boundary condition is important for non-uniform beams, and when solving it, you have to bear in mind it. Okay. So for this tutorial, it is mainly based on many examples. For this chapter, it is not easy because it involves a lot of computation, and sometimes even you look at this problem, say this problem looks, it seems that the sketch, the free body diagram given is very simple, but sometimes the solution, the answer could be very crappy, could be very ugly. Okay, so you have to be mentally prepared for such kind of cases. So in for example, you get some problem, okay, and you want to solve it, then don't think, okay, the sketch is easy, then the problem will be easy. No, sometimes for this beam deflection problems, the easy sketch could bring you a very troublesome problem. Okay, so here is the self-test and grade estimate. So still, it is just for your reference, and your results of self-test and grade estimate does not really reflect your performance in the final exam, so I will not responsible for any inaccuracy of this estimate. But anyway, try your best to work out all those 6 problems yourself before you play the solution or you watch the solution. Or even after you play or watch the solution, you can still try it again. there are still some mathematical techniques that worth you to learn. Okay, so thank you for watching the tutorial 7, deflection of beams. Seeing you in the next tutorial.